Hi, my name is Jamie Guo, and this is my video lab report for Physics 2211. In this lab, I will be examining the constant velocity motion of a rolling tennis ball. This presentation begins with a short introduction and then talks about the experimental model. I will then go into details about the computational model and finish off with a graph comparing the two. The purpose of this lab is to predict the one-dimensional motion of an object and compare it to the experimentally observed motion. Here, we will do so by utilizing Newton's second law, from which we can derive the velocity update and position update formulas to predict the position and the velocity of the ball. Before diving into my data, I'd like to explain how the ball is in constant velocity. According to Newton's first law, an object moving at a specific velocity will stay at constant velocity unless acted upon by a force of some kind. With such knowledge in mind, we have to assume that the net force acting on the ball is zero in order to achieve constant velocity. Within the model and the experiment, while the object is in motion, I made the assumption that forces such as friction and air resistance applied on the tennis ball can be ignored. The only force applied to the tennis ball is the initial push I gave it. For this experiment, the system is the tennis ball itself, and the surrounding is the ground the tennis ball is being rolled on. After carrying out the experiment, our data showed a similar trend between the experimental position and the computational position, but it wasn't identical. This can be accounted for through potential human error, and that gravity and air resistance can't be ignored. For the experimental part of the lab, I had to make use of the tracker app. I first used the calibration stick and set the diameter of an average tennis ball to be 6.58 centimeters. I then added an axis and set the origin to be the center of the tennis ball to help better visualize and follow the movement of the ball. I rolled my tennis ball from right to left, which resulted in displacement and velocity in the negative x direction. However, if I were to flip the axis around, the ball would be going in the positive x direction and result in a positive sloping position versus time graph. The speed, or magnitude of the average velocity, would be the same as the unflipped version, but the sign would just be reversed. I chose the initial and final frame of my video to be from 64 to 79 to ensure that the ball was in motion. For my data, I set frame 64 to be time 0 and frame 79 to be the final time. Within the experimental design, the only force acting upon the ball was the initial push I gave it at the beginning due to the assumptions I made at the start. After, I pointed out all of the center mass based on each frame to acquire position versus time data. While doing so, the initial position was 0.0009 meters. I was then able to calculate the average velocity using the first two data points in the average velocity formula of delta position over delta time. I found the velocity to be negative 0.585 meters per second. Here, my goal was to predict the position of the tennis ball by utilizing the momentum principle, or Newton's second law, in glow script. First, I started to manipulate the code by setting the mass of the tennis ball to be 0.057 kg, which is the average mass of a tennis ball. The ball's initial position and velocity were drawn from the experimental data from earlier, being 0.0009 meters, and the latter being negative 0.585 meters per second. The delta time for my data was 0.67 seconds, and the final time was 1 second, which we also gained from our experimental data. The net force was set to 0 as we assumed that there was no other forces acting on the tennis ball except for the initial push that I gave. Here we can justify that the net force is 0 as the ball is in constant velocity. In real life, there will be forces such as frictional force, air resistance, gravity, and the force the ground exerts on the ball. With the knowledge I have right now, these are the pushes and pulls that I can identify, which combine to have a 0 net force. Finally, to predict the position according to its time, I use the velocity update formula and position update formula obtained through Newton's second law. After all the codes were updated accordingly, I found the average velocity to be constant value of negative 0.585 meters per second throughout the whole motion, and obtained the position and time graph. After obtaining all the information, I graphed the computational position and experimental position according to its time on the same graph. Here, we saw a similar increasing negative overall trend in position. However, the experimental model seems to have a flatter slope. This makes total sense, as in our experiment, friction and air resistance cannot be ignored. These forces slowed the tennis ball down, which explains why the experimental position is closer to zero as time goes on compared to the computational position. Thank you for listening.